Now we're going to take a look at the constant velocity particle motion model, and we're going to use constant velocity graphs to write mathematical models or the equation describing the motion in the graph, and we're also going to predict the position or the time of the object given the other variable. We're going to do that both using the graph and using the equation. Okay, so here is the graph, data, and equation from the Tumblebug lab summary I did in a previous video. So just as a review, y equals mx plus b is our generic linear equation, and that describes this particular line since obviously it is linear. For the y variable, we substitute in whatever variable is on the x-axis, and that is position. So position is what we were measuring, and in physics we generally use x for horizontal position. So that's why I have an x here for the y-axis. I know it's a little confusing, just go with it. And then for the x-axis we had time, so we plug in a t there. And then the y-intercept is 1 meter because when time is equal to 0, the buggy was at 1 meter. And this is our slope, so for every 2 meters the buggy goes, it takes 1 second to do that. Okay, so just a reminder, that was kind of our generic equation, and we talked about how this slope is equal to the velocity, and that 1 meter is equal to the starting position, and that is relative to the origin, whatever we're considering 0. So here I just got to pick something to be 0, and then the buggy started 1 meter in front of that. So let's take a look at some graphs. So I already have some graphs here. We're going to figure out the equations. Okay, so first we have an orange line, a blue line. I'm showing two different types of motion on the same graph. I'm going to look at the orange line for right now. So notice the orange line is starting out here at 0, 0. So that tells us nice and easy the y-intercept is 0. And then it's ending up here. So let's start by writing out our equation. So I've got y equals mx plus b. On the y-axis is position. We're going to use x. For position, on the x-axis is time. We're going to use t. Next step, let's go ahead and find the y-intercept. Like I said, nice and easy. That's 0, 0. We can put in 0 meters here. Now in the future, do you need to put the 0 in there? You know, at one point, probably not. Right now, it's still good to put it in just so we know a initial position is 0. Perfectly fine. Okay, then for the slope, we're going to do rise over run. And that's nice and easy on this graph, so you can just pick any number to go up. What's usually nice is to pick a spot where the line crosses like a little intersection in the boxes. That's the easiest way to find the slope. So right here, we're going to go up 3, so from 0 to 1, 2, and then 3. So we're going up 3 meters on the y-axis, and then over 2 seconds on the x-axis. So for every 3 meters the buggy moves forward, it takes 2 seconds to do that. So our slope in this case, again, rise over run, is going to be 3 meters in 2 seconds. We could also have used this point out here, okay? And we could say from this point we're going to go 1, 2, 3 meters, and it takes 2 seconds to get there. So we can do this at any point on the graph. Or we could have gone from 0 up to 6 meters, and then the run is 4 seconds, so that could also have been 6 meters traveled in 4 seconds. You'll notice those fractions are the same, 3/2, 6/4. They reduce to the same thing. Okay, now in math class, they want you to leave this as 3/2, so they want you to reduce it to a fraction. This is physics. We don't care about fractions most of the time. We like decimals. So that's going to be 1.5 meters per second. Make sure you do keep the units in there. Nice and easy. You take the units on the y-axis, divide it by the units on the x-axis. If you plug in your rise over run with the units, that just works out for you right there. You don't even have to think about it. Okay, the reason we like to do decimals in physics as opposed to fractions is sometimes we want to compare velocities. So if I've got a velocity, something that's going 1 meter per second, something that's going 2 meters per second, I want to know this guy's going 1.5 meters per second. It's right in the middle. If I report its velocity as 3/2 meters per second, we don't right away have a good feel for how big that is compared to other numbers. So that's why we want to keep it in decimals. Okay, if you report it in a fraction, I'm not going to take off points, but we want to get used to using decimals. So for our orange line here, we see that this is our mathematical model. So for this particular motion, the position of the object from the origin is equal to 1.5 meters per second times the time since we started, plus 0 meters, okay? And then later we can just drop that off while we're doing our calculations. So now let's use this model to make predictions. Again, we're just with the orange line. We're going to get to the blue line a little bit later. And I put our mathematical model at the top. We always want to start with that. So where will the buggy be located 3 seconds after it started? When will the buggy be 5 meters from the origin? And where will the buggy be located 10 seconds after it started? I highly recommend pausing the video, try these out for yourself, and then restart the video and check and see if you were on the right track, okay? If you just want to watch through, that's fine, though highly recommend go ahead and practice these. So I want to know where the buggy is being located. Well, what is where is the position? So X is what I'm looking for. 3 seconds represents the time. And so with this one, let's take a look. Oh, hey, the graph covers 3 seconds. So I can use the graph. I can follow up from 3 seconds and then follow over to the y-axis. And I see I'm right in between 4 and 5. Looks close to be 4.5. We could estimate that from here. Some graphs will not be easy to estimate. So sometimes we want to use our mathematical model to do those calculations. So let's go ahead and do that. Okay, so I just take my equation from up above. And notice here I already dropped the 0 because that doesn't really matter. And I plug in 3 seconds for time. Notice also I'm including my units because here I have meters over seconds times seconds. So that tells me seconds will cancel out. I'm going to be left with meters. Hopefully you can do this in your head. If not, feel free to use your calculator. 3 times 1.5 is 4.5. And our units are in meters. Seconds canceled out. And if we were going to write this out in words, we'd say the buggy, or whatever the object is 4.5 meters from the origin. So sometimes you want to specify the starting point. Okay, now let's take a look at when will the buggy be 5 meters from the origin. So 5 meters, that's a position. And since it's from the origin, we just leave it as 5. When is a time. So we're trying to find time when position, or x, equals 5. So let's go back to our mathematical model. Or we could use the graph. How about we do the graph first? So I'm going to start over here at 5 meters, and we're going to follow that over to the line, and then follow that down to the x-axis. So I can see here that the time will be somewhere between 3 and 4. You might guess it's about 3.5. Some graphs are easier to estimate than others, but since that is in between markings on the graph, it truly is just an estimate. This is where we definitely want to use an equation to double check our estimate, as long as we have the equation. So I'm going to go ahead and plug in 5 meters for x, and we're going to leave t as our variable. Resist the urge to plug in an x here for t. I know in math class you use x's for all of your variables. We want to leave this as a t so we know we're solving for time. Just makes things a little less confusing. And then we're just going to solve for t. So we need to get rid of this 1.5 meters per second. So we're going to divide both sides by 1.5 meters per second. We see these cancel out over here. So on the other side, I have 5 meters divided by 1.5 meters per second. Now, since I have this equation written horizontally, it's a little hard to see what units cancel and what don't, but I've got meters divided by meters, so they cancel. And then I have this divided by meters per second. So seconds is in the denominator of the denominator. That means it gets kicked up to the numerator. If you need more help with that, let me know. I can go over that in more detail. So we find here that when the buggy is at 5 meters, that is 3.5 seconds after the buggy started. So last one, where will the buggy be located 10 seconds after it started? Well, on my graph, this graph goes up to 7 seconds, but really 4 seconds is the last time I actually have data for. So if we had bigger graph paper, we could extend the graph and kind of estimate where the graph would be. In this case, we don't. So you're really not allowed to add on extra, grid boxes like this. That's generally frowned upon because those are going to be estimates. It's not going to help us much. So this is a case where we really have to use our equation. And we call this extrapolating. We're basically trying to figure out what data is going to look like in an area that has not been graphed. Okay, so it's outside of where the line is. So we're going to do basically what we did before. Let's take our mathematical model from up above. We're going to plug in 10 seconds for t and 1.5 meters per second. and we find out, oh, X is going to be 15 meters. So that means at 10 seconds, so 10 seconds after the buggy started, it's going to be 15 meters from the origin. Okay, hopefully that made sense. If it did not, please send me an email or ask questions. And next, we're going to take a look at this blue line, what's going on there, because that looks a little bit different.